Hey everyone, Roland this side. I hope you all are doing well. So let's say the problem of the day.
So it's 3620. It called network recovery path. So basically, what problem says is you are given an directed cyclic graph. Okay, a directed acyclic graph. So basically, we are given a diagram of n nodes numbered from 0 to n minus 1. Okay, the graph has n nodes as values like from 0 to n minus 1. This is represented by a 2D array edges of length m, where hi represents vi. Vi cost indicates one-way communication from node ui to vi to basically it's a directed graph where each edges represent the from where it's began to where it's end and the weight of the edge. Okay, so this represents the weight of the edge, the last, the ui vi. I mean, from where it starts, from where it ends, and the edge of that. I mean, the cost of that edge. Okay, with the recovery cost. Some nodes may be offline. You are given an boolean array online where online I equal to true means I is online. Nodes n minus 1, 0 and n minus 1 are always online. Okay, so basically in our graph we have given an array called online where it says then where each indices represent the node number of that time, the node number of that node where each indices represent a node in the graph, and it says is it offline or online. Okay, it's a boolean vector. Path 0 to n minus 1 is valid. So a path from 0 to n minus 1 is valid if all intermediate nodes are present online. Okay, so we can only traverse a path if all nodes are online there. Okay, and second, the total recovery cost of age of path do not exceed, and the total cost of the path should be less than equal to k. Okay, so what basically says is basically we are given a directed acyclic graph where this is represented by a, I mean, vector called edge. Okay, a 2D vector called edge, where each edge represents the, I mean, first node, the second node where it's connected to. Okay, vi, and the cost. Okay, so if it's u and v, there is an edge from u to v. Okay, and the cost. Okay, the third one is cost, and we are given a boolean array called online where it contains boolean value where each represents the, I mean, its index 0 1 2 3. So it represents is, I mean, it's 1 is, it's 2, for example it's 3. So its represent is 0 is online or not. So for example it's offline. Okay, it's offline. 1 is also offline, 2 is online, and 3 is online. So it represents this. And okay, so to a path for a, so when a path become valid when, so let me tell this, to a path to be valid all the nodes should be online on that path. Okay, so this path couldn't can this path is not a valid path because the starting node is not online. And second of all, the total recovery cost of the path, for example this edge has cost here. Okay, so for example it's 2, it's 3. So the cost of this path from 0 to 3, considering these all are online. So, okay, the cost of this part 0 to 3 has 5. Okay, so it must less than equal to k to this part to be a valid path. Okay, so for each valid path define a score as minimum edge cost along the path. Okay, and each path has a score. For example, a path like this exists. Okay, 0 1 2 3. For example, we are considering this as a valid path considering all nodes are online and its sum does not exceed k. Okay, it's 1 to 25, for example, and k equal to 30. So total sum is less than 30. So it is a valid path, and all of nodes are online. Okay, so basically it's a valid path. So what is the score of this path? Okay, so the score of this path is the minimum edge, is the weight of minimum edge. And what is the weight of minimum edge? It's 1. Okay, so the score gonna be 1. So for a, in a valid path, the score of that valid path is the minimum edge cost of that path. Okay, we have to return the maximum path score. So basically we can have multiple valid paths. For example, this is another path, this is another path, its score is 2, its score is 24, okay, like that. So what we have to return, we have to return the maximum among this score, okay. So we have to return the max. So first of all, if you see here directly, one thing is clear. Here we are taking the minimum and then we are maximizing it. So basically what we have to do, we have to return the largest minimum edge cost, okay. So we have to return maximum the first, so we have to return max of path score. And what is the path score, okay. What is the path score? It's so path score basically means minimum edge cost, max of minimum edge cost of valid path, of the valid path. So basically, among all valid paths, we have to get the minimum among the all to get the score, and among all the score we have to return the minimum. So we have to basically maximize the minimum. We have to maximize the minimum, and whenever you see this, the first approach that comes in your mind is binary search. Okay, so how we are going to do this? So first of all, just first we knew that we are going to use binary search here. So okay, so from low to high we have to check if that exists or not. So okay, what we are going to do is we are, for example, we have a low, we have a high, and how we are going to get low and high is are going to create our adjacency list. Okay, we are going to create adjacency list, and while creating the adjacency list, what we are going to do is basically it's restore the list all connected to, okay. For example, 1 2, the weight of all connected nodes, okay. So while making this adjacency list, we have to store the minimum edge cost, and we can calculate maximum edge cost while creating this, okay. So basically we have to, this is the this is the minimum cost across the all graph, okay. So for example, it's called it L and this is gonna become R, okay. So here, from here we are going to get L and R, and what we are going to do is we are going to, while L is less than equal to R, we are going to check mid equal to L plus R minus L by 2, and if we are going to check mid, so if mid is a valid, okay. So if we had a path where mid is valid, so basically what is mid? Mid is, so for example, let me write what is mid. Here we are checking mid, that path score, okay. So we have to check basically this check function. What does is it basically tells us that there exists a path with score mid, okay. So this check function gonna tell us there exists a path with score mid, okay. And how we are going to implement that, we are going to see it later, sooner. So after that, if exists, so answer gonna become mid, and we have to maximize the score, okay, among the all. After getting the score as a minimum edge path, we have to maximize the score. So how we are going to do is we have to maximize it. So if we get it, so we are going to do L equal to mid plus 1. If this mid exists, there might another answer exist greater than this, okay. And if we didn't get it, else if this mid doesn't exist, there no way another greater one can exist, okay. So we are going to do this R equal to mid minus 1, okay. So After that, what the only thing we are left with is our check function. So basically now we have to only implement our check function. Okay, so let me tell you how we are going to do this. Okay, now we have to implement the check function. In check function, we have to check is there a score or mid. Okay, so basically what we are going to do is we are going to instead, so there can exist multiple valid paths. Okay, with, I mean, for example, its score is equal to mid, its score is less than equal to mid. For example, another path whose score is greater than mid. So basically we have to find a path is there exists a path with score equal to mid. Okay, so for example, instead of traversing every path, for example, this is also valid because it's, for example, it's also equal to mid. Okay, let's say it's also equal to mid. So for example, here are two paths. So basically instead of traversing every part, what we are going to do is, I mean, we have to find the cheapest path. Okay, cheapest part, cheapest path. And while finding the cheapest path, what we are going to do is remove every edge greater than, I mean, every edge less than mid. Okay, so if there is a edge which is less than mid, we are going to delete that edge. Okay, so for example, our mid is 5. Okay, and its edge is 1 2 3 5 6 7 8 9 10, and we have to 5, so we have to delete all this edge, and after deleting all this edge we have to find this. Okay, so basically first of all find the cheapest path. So to find the cheapest path, and while finding the cheapest path, we can also make sure instead of traversing every path, so make sure it's if cheapest path is greater than k. Okay, so they are not going to exist any path with that mid. Okay, for example, if cheapest path is already greater than k. Okay, so how we are going to expect that there exists another path which is less than equal to k, and to be a path to be valid, so it's must less than equal to k. Okay, so it must less than equal to k. So first of all we have to find the cheapest path, and we, I mean, finding the cheapest path, we are going to use is the extra. Okay, and while you using the extra, we have to take care of one thing, that we have to remove every edge which is less than mid. Basically, if we got a edge which is less than mid, we are going to continue. Okay, we are not going to, I mean, we are not going to iterate over this. Okay, so for example, so now let's, so to write the check function, if you saw this, so the code what we do, I passed the minimum score. I mean, that's, we can also call it mid. Okay, the size of n. Okay, we have to first pass the k and the adjacency list. Okay, and we called it here graph. Okay, so now we have to initialize our distance matrix. Okay, so calculate the average distance from, calculate the distance from node. Okay, what we did in, I mean, classic Dijkstra, and is, I mean, is what, yeah, min hip. Okay, and after initializing the min hip, we are going to start with 0, pushing that 0, and while it's not empty, so first of all let's see the first concept. Okay, here now we are taking the, I mean, the element and the node value of that node and the distance of that node from the, I mean, from the source element. Okay, so if distance is all, distance from the source of that node is already greater than k, we are going to return false. Okay, I mean, that's never gonna become. Okay, this, I mean, there shouldn't, there are not going to exist a path, we are simply going to return a false. Okay, and if node is equal to n minus 1, we, I mean, we reached the last node, so we are going to return true. And if any path d is greater than distance of node, we are going to continue the basic Dijkstra. If the current distance, I mean, the current distance is greater, is already greater than the what we have in our node, so we are going to skip that. Okay, because we are initializing at long max. Okay, so that's, we are going to continue, and if not, so we found a distance which is less than, so then we are going to relax that. Okay, so what we did is extra, and first, I mean, I'd set over the all adjacents, and in adjacency list I'd set over the all neighbors. So we got the neighbors, node neighbor and the weight of to get that neighbor. So if weight is less than minimum score, we are going to escape this. Okay, if weight is less than minimum score, we are not going to include that part. Okay, so that what we basically that what I meant when I said we are going to delete the path with where score is less than minimum. Okay, and if not, if weight is greater than minimum score, and if the distance until where, if what we call distance. Okay, if distance of from the starting node to this node plus the weight between the correct node and next node is less than what we actually had in distance from the starting node to the next node, that we are going to update the distance and to the another minimum value that what we got here. Okay, and after that we are going to push that until and dimple do the Dexter until after that we have simply got the we simply got this. Okay, and at last if we didn't reach to this index we are going to return false. Okay, and here the binary search I discussed. Okay, and last we are returning the answer, and if we see here it's we are creating our adjacency list. Okay, and it's a very important thing we are going to, okay, wait, I'll explain it. So okay, so for example we have a graph like this. Okay, so while creating, for example, it's A, B, C, D, E, F. For example, A is connected to B, comma D, D is connected to, E. Okay. So what we are doing is, for example, D is offline. Okay. So if D is offline, so I think we can go to D. No, we can go from D. No. Okay. Can for example, it's this. Say, can we go to D? No. Can we go from D? No. Okay. So if I mean online node, if the node from we are considering this U and V. Okay, or if either U or either V is not online, any of this is offline. Okay, we are going to skip that. Okay, for example, we are creating this edge. Okay, and D is offline, we are going to skip this. For example, we are creating this edge and D is online and E is offline, we are going to skip that, because this edge should not to exist edge between two nodes. The both of them has to be both of them has to be online. Okay, so if either any of them U or V is offline, we are going to skip that. Either we are going to push that in our adjacency list. And here, look, we are calculating the low and high. We are getting the least possible value of our edge. We are going to cheapest edge in our cost. Graph, and we are going to costliest edge in our graph, and that's we are using to maintain low and high. That's how we are initializing our the value of low and high in our binary search. And after that, we are simply doing this check answer time. Okay, so if we see the time complexity here, it's basically, so the time complexity equal to, for binary search, it's for binary it's log of n. Okay, and for inside binary we are doing the check function. So in check function we are doing the extra. And for the extra, we all know that it's big O of V plus E log V. Okay. So that's the time complexity. We have to multiply this. Okay. Because we are doing this. So that's the total time complexity. Big O of log and times V plus E log V. Okay. So that's total time complexity. And space complexity. Space complexity is gonna become big of n. Okay, we are using a priority queue and our distance matrix. So at worst it's gonna go to 2n. Okay, and yeah, I think that's the total code, and I think yeah, that's it for today. I hope you like this video, so please make sure to subscribe to TENZOR and feel free to ask any doubts if you haven't commented. Till then, keep smiling and keep coding.